All right, so we have a linear programming problem here, so take a moment to read it, pause the video, and then when you come back, we'll start writing some equations. All right, so welcome back. So as we can see from the problem, we're trying to figure out how many days each refinery should be used. So and since this is a minimization problem, and what tells us that is right here, we're gonna say Y1 is the number of days for refinery 1, and Y2 is the number of days for refinery 2. All right, so with that in mind, let's make a table to organize this information. So here's what we have. We have cost, and each refinery can make high-grade oil, medium-grade oil, and low-grade oil. All right, so we have refinery 1 and refinery 2. Refinery 1 costs $20,000 per day to operate. It can produce 400 barrels of high-grade oil, 300 medium, and 200 low. Refinery 2, a little bit more expensive to run. It produces 300 barrels of high-grade oil, 400 of medium, 500 of low. And the funny thing is, it looks like we're getting 700 barrels out of each. 700 barrels out of, in total from all of them. So here's what we're looking at. So we're looking to minimize the cost. And we know that we have constraints here. The company has orders totaling 25,000 barrels of high, 27,000 of medium, and 30,000 of low. Now, these are orders that have to be met. So that means that whenever I add these together, and that's any of the three, it has to be greater than or equal to. And this right here is my objective function. So we have basically formulated the linear programming problem just by forming this table. So if you want to try to write the equations yourself, you can. When you come back from pausing the video, I'll have the linear programming formulation all ready for us. So here it is. And keeping the table near us. So we're minimizing cost, 20,000 Y1 plus 25,000 Y2, subject to, and we just basically read off the constraints as we go down the column. So 400, 325,000, 300, 427,000, and I'm just realizing that I left off a 0 there, and 200, 530,000. And naturally, the non-negativity constraints have to be there as well. So then, how do we get this going? We want to use the simplex method to solve this problem. Even though we don't have to, it can be solved graphically, probably quite easily and straightforwardly, but we want to use the simplex method. So in order to do that, we have to convert this to a maximization problem. So here's the pieces to that. We first make the matrix form of the minimization problem. So this line right here is essentially a greater than or equal to. And you notice that the constraints go first. So notice first constraint, first row, okay? Second constraint, third constraint. And then in the bottom, we put the objective function. So this guy goes here. And notice the x in the lower right-hand corner, we're not assigning a value to the objective function, so I'm just using something that we know is going to be conspicuous, okay? To convert it to a maximization problem, we take the transpose. So to get from here to here, we're transposing. And remember, with transpose, rows become columns and vice versa. So just looking at this first row again, looking at this first row again, that became the first column in the new matrix. And then when we reformulate this as a linear programming problem, the thing to remember is these are now less than or equal to constraints, because that's what a standard maximization problem looks like. And that bottom row becomes my objective function. Notice also that we have 3 variables to the left. We started with y1 and y2 here. Now we have x1, x2, x3, okay? So putting that all together. So remember, first 2 rows are constraints, third row is objective. So I'm just going to use the standard letter for maximization problems, Z, I'm going to say maximizing Z equals 25,000 x1, 27,000 x2, 30,000 x3. Remember, this guy is just a placeholder, so it doesn't really mean anything. And then subject to the constraints, notice where the numbers come from. And then automatically, again, non-negativity constraints. So where does this land us? Well, we made the initial simplex tableau, which is right there. Notice I added the slack variables. And then remember, the first step in the simplex algorithm is identify the highest negative value in the bottom row, which is under the x3. And then we perform ratios of the right-hand side to the x3 column to figure out which variable enters. 20,000 divided by 200 is 100. 25,000 divided by 500 is 50. That's the winner. So that's our pivot, which means we're going to use R2 to combine with R1 to make a new R1. And we're going to use R2 to combine with R3 to make a new R3. So figuring out the numbers, and remember the pro tip from before, always multiply the negative by the pivot row if you have to. That's going to make life so much easier later. So I'm looking at 500 and 200, and the magic number I'm thinking is 1,000. So I'm going to take negative 2 times R2, and I'm going to add 5 R1 to make the new R1 to make that a 0. And between R2 and R3, it looks like I have to take 60 R2 and add to R3 to make a new R3. So if you'd like to pause the video and work the calculations yourself, try to get that next simplex tableau, go right ahead. And welcome back. And now that you've done the calculations, there's the new tableau. And notice we're still not optimal because we still have negative entries in the bottom row. So here we go again. Most negative entry in the bottom row is the x1 column, the negative 7,000. We perform ratios again. 50,000 over 1,400 is basically, it is the same as 500 over 14, just crossing out common zeros. 25,000 over 300 is 250 over 3. 500 over 14 is somewhere in the 30s. 250 over 3 is over 80. So that means that the 1,400 is the winner. So now we're pivoting again. And we pivot around the 1,400. So it looks like if I want to work with 1,400 and 300, magical number is negative 4,200. So I'm going to take negative 3 row 1 plus 14 R2 to make a new R2. And I'm going to take 5 R1 plus R3 to make a new R3. So here again, if you'd like to work the numbers yourself, come up with the new rows, please go ahead and pause the video. And now that you're back, new tableau, and would you look at that? We are optimal now. So this is our indicator that we are finished with the simplex tableau. So now we just have to write our solution. So now remember, the original problem was a minimization problem. So we don't so much care about what the x's are. We care about what the y's are. So the thing to recognize here is, okay, z here has the coefficient of 1. So this means that z is equal to 1,750,000. And that's the maximum value of our maximization problem, but it's also our minimum value from our minimization problem. That's that law of duality. The optimal value from the max problem is the optimal value for the min problem. And remember that the values of y1 and y2 correspond to the slack variables in the bottom row. So right here are the optimum values of y1 and y2, which tells us we should use the first refinery for 25 days and the second refinery for 50 days to minimize our total cost. And there is how you solve a minimization problem using the simplex method. Quite lengthy, not so terrible, but it is tedious and lengthy, I get it. So hang in there, keep solving, have fun with it. Thanks for watching.